The quantum revolution. Here's a wild fact: a quantum computer with just 300 qubits could process more states simultaneously than there are atoms in the entire universe. Let that sink in. Your laptop right now, it's basically a caveman compared to what's coming. And the craziest part? It's not science fiction anymore. It's happening in 2025, in labs, today. And your software development skills might be completely obsolete in 5 years if you don't pay attention to this video. I'm not trying to scare you, but imagine being a web developer in 1995 who never learned the internet was a thing, or a mobile developer in 2005 who ignored smartphones. That's where we are with quantum computing right now. Most developers have no idea it's coming. Let me set the scene. Your classical computer, the one sitting in front of you, processes information in bits, 0 or 1, on or off. That's how it's worked since computers were invented. It's actually incredible technology. But here's the problem: some problems are just too hard for classical computers. Want to simulate a drug molecule? Could take years. Optimize a shipping route globally. Billions of calculations. Predict climate patterns? Good luck. But what if there was a computer that could process millions of possibilities at the same time? Welcome to quantum computing. Here's where it gets interesting. Instead of bits, quantum computers use something called qubits. And qubits are absolutely bonkers. A regular bit is like a light switch. It's either on or off, 1 or 0. Simple. Qubits? They're like a coin spinning in the air. They can be heads, tails, or both at the same time until you catch it. This is called superposition. And it's the key to quantum's power. Here's the math that blew my mind. With 3 regular bits, you can represent 8 different numbers, but only 1 at a time. 3 qubits? They can represent all 8 numbers simultaneously. Now scale that up. 300 qubits operating in superposition can exist in more states than atoms in the observable universe. That's the exponential explosion. That's why quantum is such a big deal. But here's what physicists have been struggling with for decades. Qubits are fragile as hell. They decohere. They break. Random quantum fluctuations destroy their quantum state. This is why we haven't had practical quantum computers yet. The hardware kept falling apart, until now. 2024 and 2025? This is when it gets real. Google released a chip called Willow, 105 qubits. And for the first time, they proved something that seemed impossible. Adding more qubits actually reduced errors instead of multiplying them. They call it going below threshold. It's the breakthrough physicists have been chasing for 2 decades. But that's not even the wildest part. Willow ran a benchmark calculation in 5 minutes. A classical supercomputer would need 10 to the 25th power years. That's a number with 25 zeros. For perspective, the universe is only 13.8 billion years old. Think about that. And it's not just Google. Microsoft put 24 entangled logical qubits on a processor. IonQ ran a medical device simulation that outperformed classical supercomputers. IBM is shipping quantum processors with thousands of qubits. We're not in the maybe someday phase anymore. We're in the it's happening now phase. Let that sink in. So what's this actually going to do? Where's this technology going to change your life? Drug discovery. Pharmaceutical companies take years and billions of dollars to bring new drugs to market. Mostly because simulating how molecules interact is insanely complex. Quantum computers can simulate molecular interactions at quantum speed. What takes years could take days. Personalized medicine. Quantum could help tailor treatments to your genetic makeup. Finance. Banks are already experimenting. JP Morgan, Huaxia Bank, they're running quantum algorithms to optimize portfolios and analyze risk in ways classical computers can't. Imagine predicting market crashes or optimizing trillion-dollar portfolios milliseconds faster. That's trillions of dollars at stake. Logistics and supply chains. Volkswagen and DHL are already running pilots. They're using quantum algorithms to optimize traffic flow and delivery routes. The math is complex because you've got thousands of variables: vehicle capacity, time windows, traffic, fuel costs. Quantum can crunch all those variables simultaneously and find the absolute optimal route. No more rough approximations. Actual optimal. Batteries and energy. Tesla, other EV makers, they need better batteries. That means understanding material science at the atomic level. Again, quantum simulation. Same with solar panels, power grids, discovering new materials that don't exist yet. Quantum could do that. Cybersecurity. Here's the scary one. Current encryption, the RSA algorithms that protect your bank account, your passwords, everything, relies on the fact that classical computers can't factor huge prime numbers in a reasonable time. Quantum computers, they can. So your bank data, government secrets, medical records, if they're encrypted with RSA and someone records them now, a quantum computer in 5 years could crack them. That's why government agencies are already re-architecting their security infrastructure. You know, when we talk about quantum computing, it's easy to get swept away by the hype, the promise of solving problems that would take today's supercomputers billions of years. But let's be real, there's this massive, unavoidable issue lurking in the background, like an elephant in the room that nobody wants to acknowledge at first. I'm talking about quantum error correction. Yeah, it's the big, hairy challenge that could make or break the entire field. Picture this: quantum bits, or qubits, are incredibly fragile. A stray photon, a tiny vibration, even a cosmic ray from space can flip them, introducing errors that snowball into chaos. Without error correction, your quantum computer might as well be a glorified calculator that crashes mid-calculation. But here's the kicker: traditional error correction methods from classical computing, they don't cut it. We need something revolutionary, like quantum error correcting codes that protect qubits without destroying their quantum magic. Think of it as trying to fix a house of cards in the windstorm without knocking it down. Researchers are racing to develop these codes, stuff like the surface code or topological qubits, that can detect and correct errors in real time. It's not just tech, it's a fundamental rethink of how we handle information. And if we crack it, quantum supremacy isn't a dream, it's inevitable. But if we don't, well, that elephant might just trample the whole party. What do you think? Will we tame this beast, or is it the Achilles heel of quantum computing? Drop your thoughts in the comments below, and don't forget to like and subscribe for more deep dives into the quantum world. Here's where you come in. If you're a software developer, this isn't just interesting, it's career-defining. Because quantum computers don't run your traditional code. You can't just compile Python to quantum circuits. The entire algorithm design is different. You have to think probabilistically instead of deterministically. Instead of this input produces this output, it's this input produces a distribution of outputs you measure, and the quantum state collapses into one answer. In the near term, we are talking hybrid systems. Your classical code runs on regular computers, and when you hit a problem that benefits from quantum optimization, simulation, machine learning on sparse data, you ship that specific component to a quantum processor, like how you might offload GPU tasks today. But the programming languages themselves are evolving. Q# from Microsoft integrates right into Visual Studio. Qiskit from IBM is Python-based and the most popular framework right now. Here's the beautiful part: if you know Python, you can start learning Qiskit today, for free. You can run quantum programs on IBM's cloud quantum computers, also free. You don't need $1 million quantum chip in your garage. Circ from Google is lighter weight and research-friendly. These aren't just libraries, they're entire new paradigms for thinking about computation. You can start learning right now. Let's talk money and opportunity, because this is where it gets exciting for your career. In 2024 alone, $2 billion flowed into quantum startups. That's venture capital, big money, and hiring is happening. Google, IBM, Microsoft, IonQ, Rigetti, they're actively recruiting quantum software engineers. Quantum engineers are getting paid 30 to 50% more than classical developers for the same experience level. Why? Supply-demand gap. There's enormous demand and almost nobody with the skills. Most demand is in finance, pharmaceuticals, defense. Those sectors are betting billions on quantum advantage. They need people who can design quantum algorithms and integrate them into classical systems. Here's your action plan if you're interested. 1. Learn the fundamentals. Linear algebra, complex numbers, quantum mechanics principles. Don't panic, you don't need a PhD. There are great online courses. Start with Qiskit tutorials or IBM's Quantum Academy. 2. Pick one framework and build something small. Grover's algorithm is a great starting project. Variational quantum median-silver, VQE, is another. Use free cloud resources. Get your hands dirty. 3. Contribute to open source. The quantum community is collaborative. GitHub has tons of quantum projects. Contributing looks amazing on a resume. 4. Build small projects using Grover's algorithm and VQE simulations. Get your hands on it. Lastly, network. Join quantum computing Discord servers, Reddit communities, LinkedIn groups. Follow people doing this work. Start today, not next month, not when you have free time. Today, because the people who start now, they'll be the senior quantum architects at major tech companies in 5 years, and they'll be getting calls from recruiters constantly. But I need to hit you with a serious warning, because this isn't all positive. Post-quantum cryptography is a crisis in slow motion. Your company's sensitive data, if it's encrypted with current algorithms and someone's recording it now, A quantum computer could decrypt it in 5 years. That's not hypothetical. NIST has already standardized post-quantum cryptographic algorithms. Governments are mandating crypto agility, the ability to swap out encryption quickly. If you work in security, defense, government, finance, this is already your problem. Your company needs to audit their entire encryption infrastructure and plan for migration. It's complicated. It's expensive. But it's coming. This is why the first quantum advantage might not be in drug discovery. It might be in cryptanalysis, breaking codes. It's the nuclear option of quantum computing. So why does this matter to you? Really, you're at an inflection point in tech history. We had the computer revolution, then the internet, then mobile, then AI, and now quantum. Every one of those inflection points created massive economic value, and it created it for people who understood the technology early and could apply it. If you learn quantum computing now, in 5 years when it's mainstream, you won't just have a unique skill, you'll have deep understanding of how to design systems with it. That's worth serious money and serious impact. The other option? You keep coding the same way you did in 2020, and in 2030, you're explaining to your manager why your classical algorithms can't solve problems that quantum solved 3 years ago. Don't be that person. The quantum revolution is coming. The question isn't whether it's happening. The question is whether you'll be leading it or playing catch up. I know what I'd choose. Start learning. Pick one resource, maybe Qiskit tutorials. Spend 30 minutes this week. Run your first quantum program. Go to Microsoft Q# and execute Hello World. It takes 5 minutes. Thanks for watching. See you in the next quantum deep dive. Resources related to Microsoft Q#, Google Circ, IBM Qiskit tutorials are given in description. What excites you most about quantum? Comment below. Like and share this video. Tag someone who needs to see this. Your developer friends, your manager, your team lead. Comment below. What would you build if quantum computing were available today? What problem would you solve? I'm reading comments and replying to the best ones. And subscribe. We're covering quantum in depth here. Error correction, specific algorithms, career paths, the whole journey. You want to be ahead of the curve, you need this channel.